There are many techniques to design differential amplifiers. One example is the Darlington differential amplifier circuit that is discussed in this video. It is implemented in one stage in this example. This one stage has a core Darlington BJT transistor pair on the left side, and also at the right side of the circuit. The circuit has a mirror symmetry with respect to the center, and then we have, aside from transistors T1, T2, T3, T4, we have BJT bipolar junction transistor T5 here that serves as the current source at the bottom of the circuit that provide a DC current to feed the two left and right mirror symmetric branches, so they have the same DC current value. And at the input of the circuit we have a small signal V1 and V2, so there are small AC voltages, A sine omega t, A being just a millivolt or tens of millivolts at the input of the circuit, and omega is the proper frequency for these AC signals. We want to see what is the output voltage that is decoupled from the circuit by this decoupling cap, and we want to see how the circuit is working, and then how to find and compute the differential voltage gain of the circuit, also differential input impedance of this differential amplifier, and finally common mode rejection ratio, how much is it. We make the assumption that the beta for all BJT transistors or current gain is 100, which is okay assumption for nominal bipolar junction transistors. Okay, so it's a dual supply design, 10 volt and negative 10 volt, and the value of resistors are provided, nominal values. And let's do the analysis. So let's start with the DC analysis. So for that, maybe before that, let me just describe how the circuit is working. For the differential, let's say voltage, the V1 is applied like this, as let's name this as, for example, minus V over 2. Just a name for that, and or plus V over 2. And then for V2 in differential mode, we are effectively just doing exactly negative V over 2. So when we are in the cycle, that signal is increasing sinusoidal, we are decreasing at the V2 side. So what means that while we have mirror symmetric DC currents that are flowing through these branches, we will find them. So these are DC bias currents. Those are, let's say, sizable currents. But there is AC, a small signal current that went during this cycle, that input voltage at the V1 side, which is connected to the base of T1. When that is increasing, it injects an AC current. Let me use a different color. So it injects a AC current, a small signal AC current, on top of the blue DC. So these two add together, but the blue one is much larger. But then, because exactly whatever amount the base voltage is increasing for T1, we can see that the base voltage for T2 connected here is decreasing actually. So whatever happening in terms of the magenta current adding to, let's say, the blue current for T1 to T3 transistors, what happens is exactly that current is being reduced or subtracted from the DC current of T2 and T4 transistors. So what I'm saying is when we are doing differential analysis, it's as if same magenta current that is going through T1 and T3 is going to T4 and T5 like this. So from perspective of differential analysis, it's as if this current keeps going on from V1 to V2, as if T5 doesn't exist, as if this node is AC grounded effectively because of mirror symmetry in the circuit, and because we are applying plus V over 2 and negative V over 2 on the other side. So the AC voltage here is 0. That's why this is referred to as virtual ground for AC in the AC analysis. Okay, so this current going this way, of course, knowing that the AC current of collector is roughly the same as AC current of emitter, so whatever magenta current is going as I'm showing, the equal amount AC current going like this, causing a voltage drop across RC AC wise like this. And that should loop around effectively, because we are saying this magenta current is going this way through T4 and T2, so that means the same amount should go like this, AC wise, a small signal, through RC, which means this voltage drop. And because of this cap, you can see here it's a bypass cap, so it means AC wise this is shorted, so this node AC wise is virtual ground. So therefore the output voltage, which is a single-ended output voltage, is basically just this plus minus between the output and AC ground, or virtual ground AC. So this voltage drop with this polarity, which is matching exactly the desired polarity for V out, is what we are expecting. Therefore, with respect to V1 minus V2, the voltage gain should be a positive value. So that's what we are going to find. So that will be the, I'm going to write it here. So the let's say differential voltage gain, so it's V out over delta V, which is V out over V1 minus V2. It's what is we refer to as AD, differential gain, voltage gain of this circuit. That's a positive number because of the scheme we have. So V1 minus V2 wise to this connection to V out is a positive voltage gain. So I'm going to write it here just so that we remember it. Okay, good. So here it's a positive voltage gain. Positive gain. Now for common mode analysis, what we do is instead of plus V over 2 and minus V over 2, we are going to apply same voltage. So I'm going to apply exactly A sine omega t, which I refer to it as V, and I'm going to apply exactly same thing here, A sine omega t, which I refer to it as again V. So we apply voltage V on both sides for common mode analysis, not difference mode, common mode. And then we want to find V out again with this polarity as a function of one of the V's. So what we say is this is difference mode analysis, differential mode, and for common mode of, let's say, differential amplifier, what we say is we want to find V out as a function of let's say one of the voltages, which we refer to as the V1 plus V2 over 2, but since V1 and V2 are the same thing as V, basically it means V out over V. As we are increasing the voltage V, it is injecting, in this example now, it is injecting an AC, because when we are increasing the voltage V, what we are doing is we are increasing the base voltage, which means we are injecting a current like this, a small signal AC, that is added on top of the blue signal DC, blue current DC. So we have additional current going through T4 and T2, which means as a result we are also having additional AC collector current going through RC. This time it is causing a voltage drop like this, which is counter the voltage drop that is for V out. So therefore the common mode gain with this definition here is a negative gain, so which referred to as AC, a common mode, is a negative gain. Okay, so the last step for CMRR, or common mode rejection ratio, so common mode rejection ratio, which is an important KPI for differential amplifiers and many op-amps that benefit from the first stage differential amplifier as an example, is just absolute value of the differential gain, the common mode gain to common mode gain, and then we have this as whatever we find for the value of these guys, we need to just do this division and find the CMRR. So I'm gonna just move it here as a reference. We expect CMRR to be pretty large, on the order of tens or tens of thousands for this amplifier. We want it to be practically, ideally we want it to be infinite. So as the larger the better, which means the smaller AC or common mode gain, and the larger the difference mode gain is more desired. So larger CMRR is what we want, and a smaller AC is what we want. Ideally AC we want to be 0 in denominator. Okay, so let's just now focus on the last thing, which is the input impedance. So for the input impedance is differential mode input impedance. So that means I'm going back to the concept of applying this signal and also applying this signal here. So if I do that, then from perspective of these entry nodes, so maybe I use a different color so that it's clear. So imagine if I think of the circuit as if I'm looking from perspective of V1 and V2, as if I'm looking into this green portion. We know that we just talked about it in differential mode analysis. This node at the center is virtual ground for AC, because as was discussed, it means there is this current that is flowing in and going through all 4 transistors and not going through T5 AC wise, so as if T5 is not there. Okay, so we want to find that let's say input impedance. To achieve that, I'm gonna apply V1 and V2 in the form of two voltages, that is V and negative V, and then I'm going to find the current IB, the resulting current, and then I am going to just use the standard definition that input impedance of differential amplifier R in D is equal to the delta V that we apply, which is divided by, of course, the current of the base as a result of that. And this is a small signal, by the way, because this is the small signal differential input impedance. So we need to be careful. We are talking about a small signal analysis. So the delta V divided by the resulting change in IB, or basically the AC current. So let's put it this way: change in the base current of T1 or T2, which I'm referring to as let's say V1 minus V2, that's the change in voltage at input, divided by the AC current of base, which is basically change in the DC current. So that is the meaning of the R in differential that we want to find here. Okay, so now that we understand what are the things we want to find and how the circuit is operating, let's just do the DC analysis. So I'm going to do the DC analysis, and then I'm going to find the answer for these important things, including differential gain, common mode gain, CMRR, and R in D. So those are the questions I'm going to answer. Okay, so let's start with the DC analysis. So DC analysis quickly. To do that, let's focus on the current source portion. Quickly again, we have negative 10 volts, so that negative Vs is here, negative 10 volt. As it looks like as if we have a series effectively of R1 and R2, so it's a voltage division for negative 10 across R1, R2. Of course, I'm making the simplification that the current of base of transistor 5 is negligible. We need to double check that. So for now, let's make the assumption that that is the case. Voltage of base of transistor 5 can be computed like voltage of base of transistor 5 equal to the negative 10 volt, this guy, doing a voltage division across R1 and R2, so it's going to give us R2 divided by R1 plus R2. And substituting 3.3K, 1.5K, we will get roughly negative 6.9 volt at the base of transistor 5 here. We have plus minus 0.7 volt drop, so from negative 6.9 we get to here. Let me just write it. Maybe the better place to write it is here. At the emitter of transistor 5 we get to negative 7.6 volt. because of the 0.7 drop. And then we have across 1.2K, the R3, we have on one side -10, on the other side -7.6. So effectively that means a voltage drop like this, VR3, equal to 2.4 volt. So I can find the current that is passing through this resistor, so IE5 DC wise. So I'm going to write that as a result, IE5 is equal to, which is roughly equal to the collector of transistor 5 as well. So IC5 is roughly equal to VR3, the voltage across this resistor, divided by R3, which is 2.4 divided by 1.2. That's going to give us exactly 2 milliamp. Okay, so we found this current. We found this current to be 2 milliamp. Okay, this is a 2 milliamp current. Half of it going through this branch, so half of it going like this, 1 milliamp, and the other half going like this, DC of course, so 1 milliamp. There you go. And since that's the emitter current for T4 or for T3, I can find the currents, so 1 milliamp here, then divide by 100 beta, the current gain roughly, we get to 1 milliamp divided by 100 will give us 10 microamp. That would be the IE DC for transistor 1. This is IE DC for transistor 3, and also for 2 and 4 as well. Alright, so therefore the base current, not AC, so let's be careful that I am talking about DC current. The current of the base DC current will be 10 microamp divided by 100 beta, which will result in I base DC equal to, of course, it would be 0.1 microamp. So we found the base, and of course, and given RB 100 kilo ohm, this guy 100 kilo ohm, so that means there is a voltage drop plus minus DC, which is 100 kilo ohm times 0.1 microamp. It's going to be 10 millivolt. So 10 millivolt DC drop across RB. Basically, it means the DC voltage of the base of transistor, so DC voltage of base of 1 is equal to negative 10 millivolt, which is negligible. We can say effectively 0. Okay, so on top of that, what I see in the circuit is plus minus, let me write it here. So plus minus VBE of 0.7 volt, and then plus minus VBE, another VBE of 0.7 volt. So from negative 10 millivolt, I have 1.4 drop. So here is negative 1.41 volt. Let me write it clearly so that there is no mistake. Negative 1.41 volt. And we have 1 milliamp going through 10 ohm. So that's another 10 millivolt. So plus minus 10 millivolt. So that means this node finally is minus 1.41 and minus 10 millivolt. This node is finally voltage emitter, let's say voltage of common node, whatever it is, minus 1.42 volt. Okay, we found the voltages, and the last step is just finding the voltage drop across RC DC wise. So 1 milliamp DC is going through it. It's 5.3K, so that means we have a DC voltage drop of, let me write it here, doesn't matter for these guys. So we have a DC voltage drop of, going back to the same color I was using, across this guy 5.3 volt. Starting from 10 volt here, that means the collector DC voltage, V collector DC, is going to be 4.7 volt, which is a very good bias point because it's almost midway. We are very good in terms of the maximizing dynamic range or swing at the output of the circuit, even though we might not need it. So okay, we found the DC, all the DC information. So let's now do the R in. So I want to find R in, because as soon as I find R in, then I can answer the question for the differential gain. So for R in, so now we are doing AC, small signal analysis. Okay, so to achieve this one, I am going to start with R in, and I can say R in small signal in differential mode, as was discussed, is simply the V1 minus V2, the delta V and V1, V2 are small signals, divide by, let's say, the IBAC, which as I wrote here is simply the delta V between V1 and V2, and with respect to the change in the base current. Okay, this delta V is the V1 minus V2. What is that? We have VBE of T2, VBE of T4, VBE of T3, VBE of T1, and also the voltage drop across these two RE resistors. So, but there is a mirror symmetry in the circuit, so we just need to focus on change of the three voltages here: the base emitter T1, base emitter T3, and the RE voltage drop AC wise. So that's all we need to do. So I'm going to write it this way. It's going to be 2 times the change in the base emitter voltage of transistor T1 with respect to, of course, the change in the base of transistor. This is base of transistor 1. Change in the base of transistor 1 plus the change in base emitter of transistor voltage of the base emitter of transistor T3 with respect to still the change in the IB of base 1. And finally we have the change across RE, so that would be simply RE and then the change RE times the change in current is change of voltage across RE, and then the same thing. So we have, let me just put it this way. Okay, this guy is obviously beta squared, because from this base we have to multiply IB to get to emitter here, and another multiplication to get to emitter here. So 2 times multiply beta, which is beta square. So this is beta square, obviously. This one, let's start with this one. This one is easy because that's coming from Shockley p-n junction equation. So I'm gonna write it here quickly because I need it. So rather than using a memorized formula, I'm just computing quickly. So Shockley p-n junction equation says that for transistor T1, I can say the I emitter of this transistor is equal to roughly, let's put it this way, is roughly equal to saturation current of transistor e to the power VBE divided by VT, the thermal voltage. Thermal voltage is 25 millivolt, assuming the p-n junction is at room temperature. Okay, so what I need to do is we need to take a, let's say, the partial derivative or derivative of IE with respect to the base emitter voltage, which if you simply compute this one is very straightforward. We get IE divided by the IE divided by VT. So I'm going to write here VT is the thermal voltage and is roughly 25 millivolt at room temperature for p-n junction of the BJT transistor at room temperature. Okay, so of course when we find this, it's the same as we say for a given transistor, we can inverse it. So we have, let's say, the change in the base emitter voltage with respect to change in current. The emitter current is Vt over IE. IE is the DC current, but this is the AC change. So it depends on DC bias basically. Okay, so this is what I needed. Going back here, I know that the base of 1, transistor 1, is the emitter of the current of emitter divided by beta. So what I can write is 2 times beta change in the base emitter current voltage divided by change in emitter current roughly. And the same thing here. This is base 1 here. I need to get to, for this transistor, which is, this is about transistor 3, I need to get to IE3. So that means I need to take care of beta beta multiplied to get from IB to IE3. As a result, I can just write beta square the change in the base emitter of transistor 3 divided by change in emitter of transistor 3 current, RE times beta square. Okay, so if I substitute for these guys, I get 2 times, and for this one I can play the same game. Here I have the Vt over IE for transistor 1. So this is for transistor 1. So therefore it's beta using formula 1, let's say, equation 1. So it's Vt over the DC current bias of transistor 1. This one is beta square Vt DC current bias of transistor 3 plus Re beta square. Okay, and of course IE1 is IE3 divided by beta. Remember that IE1 is here 10 microamp and IE3 is here 1 milliamp. So obviously IE1 is 100 times less than IE3. So I am going to write it here, is equal to, maybe I just here, 2 times beta square Vt divided by IE3 instead of IE1. And then again, same thing, beta square Vt divided by IE3 plus Re beta square. So in summary, what I get, remember we are computing the input impedance in differential mode. So Re equal to just a simplified version of this, which is 2 times, and again 2 times, and I can factor out beta square from everybody. So therefore let's put it outside. So 2 times beta square times 2 times Vt divided by IE DC of transistor 3 plus Re. That's it. We found the formula. I mean, if you go back to applying the, let's say, the memorized formula, this is effectively, if you use the hybrid model for BJT transistors, then people like to refer to it as this as HIE or HIB. So here it's as if we have an effective resistor observed for the base emitter of T1, an effective resistor observed for base emitter of T3, and then the value of these resistors would be each Vt over IE3 if we reflect them from emitter 1 to emitter 3 to put it in series with the resistor of transistor T3. I just didn't want to rely on formulas and sort of memorize. I just wanted to really quickly drive it and show that logically we can, and using again first principle, we can actually quickly drive it and find it. So we found the input impedance in differential mode. If you want to substitute, this is equation 2, so I'm going to name it as equation 2. And if we want to substitute for these values, we can quickly find it. 2 times 100 beta squared, and then 2 times 25 millivolt for the terminal voltage VT, divided by IE3 DC bias for basically current of emitter of transistor 3, which is 1 milliamp, half of the 2 milliamp current source. So that would be 1 milliamp plus RE, which happened to be 10 ohm in this example. It depends on what sort of application we have. So as an example, 10 ohm for RE. So this is 50 ohm. So the answer becomes 2 times 60 ohm, which is 120, and then 120 times 10,000 will give us 1.2 mega ohm. Okay, so that is a very interesting outcome. So we have 1.2 mega ohm input differential impedance from perspective of differential mode V1 minus V2. So that's a sizable input impedance. That's one of the benefits of this Darlington differential amplifier design that enable us to achieve a very large input impedance for the BJT input stage, if op-amp is designed like this instead of the, let's say, FET input stage. Okay, so what else? I can quickly find the AD or differential gain now. How do I do that? I use this formula for the small signal differential mode voltage gain. So AD, as was mentioned, is equal to, let me change the color so that there is a little bit of a contrast. So AD is the, let's say, change in the output voltage as a function of, so change in the output voltage as a function of change in the delta V or input voltage. So we can just say that is basically change in output voltage divided by change in, let's say, current of, I'm just dividing both numerator and denominator by the base current. So it would be as if you're saying, okay, let's find the resulting current. So there you go. This one is, as we talked about it here, is just R in. So as expected is change in output voltage versus change in base current, which you can substitute for it quickly. This is R in by definition of R in. And change in output voltage as a function of the current, of course we can say it's beta squared change in output voltage divided by change in collector current for here. As if you remember, I said the differential gain is positive, so there is a AC current going like this, counteracting the DC current in differential mode. So it's beta squared. Reason we see beta squared here is because I said multiply both numerator and denominator here with beta square. Beta squared times IB, or change in IB, is basically change in overall IC, and then divide by R in differential. This thing here is simply the AC current that is flowing through RC. So is just beta square RC divided by R in differential. Okay, so that is the formula for the differential gain. Let's try. For instance, if I just substitute, I can just substitute using equation 2 before even trying to compute it. So equation 2, if I substitute, I have basically for R in D, I'm substituting this one. It has beta square in itself in denominator, and that would cancel out with the beta square in numerator. So what I get is the AD, or differential mode gain, voltage gain, is simply RC divided by 2 times VT over IE3 plus RE. So that's the alternative formula. If I substitute for these values, we can do that. So it's going to be 10 to the power 4, which is 100 square, times RC, which is 5.3K, 10 to the 3, and then divide by R in, which is 1.2 meg. Effectively, this is calculated times beta square. So 1.2, 10 to the power 6. So if you try that, we end up with about 44. So it would be 53 divided by 1.2. So 53 divided by 1.2 will give us, just to do it quickly, 53 divided by, I'm trying to make sure that the 44 number I said is a valid number. Okay, so it's going to be 44 roughly, approximately. That's the AD in this specific circuit. Now let's deal with the AC or common mode gain. So we found the differential mode gain. So the next thing is finding the common mode gain, and I am trying to just double check with a calculator, so making sure that I had it correctly. 53 divided by 1.2 is 44 roughly. 44.1.6 or 17. Let's say 44.2. Maybe that's the most accurate thing to say here, practically speaking. There you go. Okay, so what about the voltage gain for the common mode? So this is differential mode. Differential mode. So what about the common mode voltage gain, AC? Well, that is as was briefly mentioned. So for AC, we have to apply same voltage VV, and then from there we have to find the resulting output voltage. So basically V out, change in V out as a function of change in V. So it would be change in V out as a function, because it's an AC signal analysis. So what is it? If we apply the same voltage as a part of the common mode gain analysis, so same voltage on both sides, what happens is the circuit has a mirror symmetry. So I know that the both branches, they have the same DC current, 1 milliamp each. But then in the common mode AC analysis, what happens is we also have the same AC current flowing. So same AC current flowing. So I don't need to analyze both branches, because as if from perspective of input V, I have same sequence of the effective resistor or resistance of the transistor T2, the effective resistance of transistor T4, the impact of RE, all of these as we discussed ported to the emitter side, and then finally we have the 2 times the effect of, let's say, whatever resistor equivalent impedance observed from collector of T5. And that's going to be large, because this transistor T5 is boosted because there is a resistor and AC grounded. See, this cap is the bypass cap. That AC vise is short and would ground this node to AC ground, virtual ground. So therefore what happens is there is a R3 in the emitter of a transistor T5, sort of a degeneration, and that results in boosted output resistance for T5, which is going to be on the order of mega ohm, couple of mega ohm actually. But what is important is there is this current, as I said, AC vise, and this current AC vise. So from perspective of 1 voltage, it's as if the value of this resistor, neglecting the other voltage as if it's not there, it feels this is like twice, because the voltage drop across that is twice. So therefore what I'm trying to say is, maybe I put it this way, maybe the best way I can say it this way, the R in, let's say from perspective of one of those applied voltages in common mode, is equal to remember in the difference mode differential mode, we had this equal to that, so hence we had the factor of 2 involved for the differential input impedance. So that's why we have a 2 here. In the common mode, we only have 1, not 2, so it's going to be beta square 2vt over IE3 plus RE. So that's the impact of just these three guys. And then we have twice the observed impedance from the collector of T5 toward ground, so AC wise. So I'm going to write it here, plus 2 times the R resistor from the collector of transistor T5 with respect to AC ground. This one is a little bit tricky. It requires a little bit of a time, but it's well known that when we have, let me just write it here. So when we have a transistor like this and emitter grounded, then the equivalent resistor observed from collector is simply RO of transistor, BJT. And in this case, if I shift it so that I can write it, in this case, RO is just well-known early voltage of BJT transistor from early effect divided by the, let's say, roughly emitter or collector current, DC. And that's coming from the IV curve of the BJT that basically it's like this. This is the current of, let's say, collector or emitter. As I said, is roughly the same as current of emitter for large enough beta, which is the case here, divided by collector emitter voltage. So this is the look of the IV curve for BJT transistor. And if we have this stretched out or extended, this is what is referred to as minus VA, or early voltage due to early effect, usually on the order of 200 volt to 250 volts. So in this case, let's make the assumption is 200 volts. So and because the DC bias point in this case, let's say voltage of collector emitter, and we're talking about transistor T5, as you can see, the DC is minus 1.4 in collector, and it's minus 7.6 in emitter, so we're talking about roughly 6 volt approximately. So this is 6 volt and this is 2 milliamp. So 6 volt versus 200 volt is negligible. That's why we just sum it up saying this tangent, which is RO, is simply just the early voltage, which is completely sizable compared to 6 volt. We can neglect 6 volt. So VA divided by the 2 milliamp. That's basically computing this tangent, which is the RO. So, okay, that is the case. But when we have the, let's say, the resistor in the emitter, things become a little bit more complicated. It's not difficult to calculate it, but we have effectively a resistor in base, AC wise. We have a resistor in emitter, which is in this example 1.2 kilo ohm, and then we want to calculate this. In this example, without the resistor, we would have had 200 volt early voltage divided by the 2 milliamp, so we would have had 100 kilo ohm just for RO observed like this, which is pretty large. Now, when we have RE like this, then we will end up with approximately we will end up with RO times 1 plus REGM, or GMRE. GM is the transconductance of the BJT transistor, which is, let me put it this way, GM is, as I briefly mentioned, transconductance is just, depending on the DC bias, it's going to be equal to the roughly DC current IE divided by the thermal voltage. So if it is 2 milliamp divided by 25, it's 1 over 2 over 25. So GMRE And because of presence of RB with the specific value we have, which is 1.5 and 3.3 kilo ohm, this one is turning out to be, if RB was not there, I could have just written that RO times 1 plus GMRE, but because of this RB of roughly overall 1 kilo ohm, which is the same size as this guy, this will turn out to be on the order of just approximately this R out is RO GMRE over 2. So if we compute this, we will end up to, and if we substitute for IE 2 milliamp and VT 25 millivolt, we will end up to finding that this guy is about 48, 49, and this guy is, as I said, 100K. So effectively 100K times 49 give us roughly 4.9 mega ohm. So that's pretty sizable. That means this resistor here is basically R out, let's say R collector 5 is roughly 4.9 or 5 mega ohm. That's completely going to dominate every other thing. So we're talking about this guy being on the order of 4.9 mega ohm. So it's gonna just dominate everything. This becomes nothing compared to it. Of course, this needs to be divided by beta. So we need to port it to reflect it to emitter. So it would be nothing compared to this guy. Okay, so why did I calculate this? Because then the current of the common mode at the emitter side is the basically the applied voltage, which is V divided by this R in common mode. And then this current, as we talked about it earlier, is AC current is moving like this, which is counter the direction, and that's why we said the AC common mode is going to be a negative voltage gain. So I'm not going to repeat that, but that's what we know. I'm gonna just write it here. So we will have minus, so we will have basically the let's say A common mode equal to minus IC times RC. So this IC is passing through this RC, and therefore it results in an output voltage drop in common mode. Substituting for what I just wrote, we end up computing the common mode AC, which is change in output voltage as a function of change in common mode voltage at input, which, as I said, we can repeat the same game we played. So dividing both numerator and denominator by changing the current of the collector or emitter doesn't matter, and we will end up computing that this is equal to RC over effectively, as I said, this whole thing, so over R in common mode, but then this is nothing compared to RC, 2 times RC5. So I'm going to completely neglect this compared to 2 times RC5. RC divided by 2 times R collector transistor 5. To avoid confusion, let's use a small letter R for this guy. So this is basically R collector transistor 5. Okay, that's the small signal common mode gain, which if we compute it, it's going to be very, very small. We're talking about 5.3K here, divide by 2 times 4.9 mega ohm, which is just humongous. I mean, it's just on the order of, we're talking about 1 over 2000 basically, roughly, for the common mode attenuation. Basically there is no gain as expected. So finally CMRR is the absolute value of the differential mode gain to the common mode gain, which in this case is 44 divided by 1 over 2000. So it's if you want the immediate calculate an absolute value, I don't care about, let me just make sure I'm not making a mistake here. Minus here, and let's not forget it's a negative, minus, and then minus 1/2000. It's a negative voltage. Okay, and let me shift this so that I avoid confusion here. So this would be the answer for what I computed earlier. Okay. Now, if we want to calculate this one quickly, it would be 44.2 divided by 2000. Divide by 1/2000, sorry, for the A common mode. And that's not difficult to compute, of course. So we end up with 88 and then 4. So basically, we end up with 88,400 for the CMRR, which is pretty large. If we take usually in the data sheet of op-amp, CMRR is reported in dBi, so we take a 20 log 10 out of this guy, for example, and then we report that. It's pretty large and sizable. That's very good. But if we want to find the formula for this guy, rather than the value, then let's substitute AD from what we found here. So from, let's say, equation 3. So from equation 3, and for AD, and from and equation 4, let's say. So I'm going to apply equation 4, this one, for AC. So equation 4, then we get there is RC in both equation, so it would cancel out each other, and as a result I get just simply 2 times RC5, which is this one here. I'm going to substitute for it, that one. This is equation, say, 5. So 2 times RC5 divided by 2 times VT over IEDC3 plus RE, and then 2 cancel out 2, and substituting RC5 using equation 5 here, in this example it roughly become just R out of, or RO of the BJT times 1 plus GM of transistor 5 in basically the current source transistor, RE divided by 2, and then divide by 2 times thermal voltage of PN junction at room temperature, RE. And this is effectively same thing as we computed here by substituting values for CMRR, or common mode rejection ratio, of this differential amplifier. Okay, this has been extensive analysis. I hope that this example is helpful in terms of showing how we can deal with this kind of a design problem. Thanks for watching.